All right, now we are going to start talking about the binomial theorem. We're going to get into the binomial theorem and we're going to work our way there. But first we're going to talk about binomial expansions. Okay, so if we take, for example, a plus b squared. Okay, and a plus b squared, we've done this using the FOIL method, right? You've done this probably using, or what we call the distributive property, which is more accurate. So if we use the distributive property, we can get a squared plus 2ab plus b squared. And this expression, a squared plus 2ab plus b squared, is called the binomial expansion of the quantity a plus b quantity squared. Now, we could also, oops, mistake. We can also do it similarly with a plus b cubed, right? So we can write a plus b cubed as just a plus b times the quantity a plus b squared. And we know what a plus b squared is, right? So we could say this is just a plus b times a squared plus 2ab plus b squared, right? And then we could use the distributive property again by distributing the a to each of the terms, and then distributing the b to each of the terms, and then adding up all the like terms, and we would get what? A cubed plus 3a squared b plus 3ab squared plus b cubed. But what if we expand this out to, let's say, a plus b to the fourth, right? We would do something similar. But what about the general term or the general expression a plus b quantity raised to the nth power? Well, we get an interesting pattern. What it turns out is that this follows the coefficients of these. We'll get to the expression later, the exponents later, but the coefficients follow an expression. It's actually a triangular array of numbers called Pascal's triangle. Okay? And so if we notice something, and I'll just write this here for a moment. Okay, so we have a plus b to the 0 equals 1. A plus b to the first power equals a plus b. A plus b to the second power equals a squared plus 2ab plus b squared. And then we got a plus b cubed, which is going to be a cubed plus 3a squared b plus 3, ab squared plus b cubed. And then if we do a plus b to the fourth, that's going to be what? A to the fourth plus, 4a cubed b plus 6 a squared b squared plus 4 ab cubed plus b to the fourth. And so we notice, if we look at the coefficients, we get what? The first coefficient here is just 1, it's just constant. The second row, so here the exponent is 0, we get 1. The exponent is 1, we get the coefficients 1 and 1. And then here, a plus b squared, we get what? The coefficients are 1, 2, 1. And then the coefficients for a plus b cubed is what? 1, 3, 3, 1. And the coefficients for the last one, where the exponent is 4, is what? 1, 4, 6, 4, 1. And so what you notice, or you might notice, is starting with the third row, notice it goes 1 and then 1, 1, and then notice that these two coefficients add up to this one, and we get 1, 2, 1. And then we get these two coefficients adding up to 3, and these two adding up to 3, and we get 1, 3, 3, 1. And then these two add up to 4, and these two add up to 6, and these two add up to 4, and we get 1, 4, 6, 4, 1. And you can guess what the next row would be, because it's going to be 1, 5, 10, 10, 5, 1. And the next one would be what? Well, you get the idea. And so this is called Pascal's triangle. Named after the famous French mathematician Blaise Pascal. Okay, so now let's do an example. See you next time.